Sun is the ultimate source of energy for all life on Earth. Harnessing this boundless energy from the sun, we have our primary architects of life, the producers. These producers, such as plants, have a remarkable ability to capture sunlight and create their own food through a process called photosynthesis. Moving up, we have herbivores such as grasshoppers, which feed exclusively on producers. The next level feature carnivores like frogs. They feast on herbivores, maintaining balance in the ecosystem. And then we have large carnivores such as snakes, which feed on these animals. At the top of our pyramid, we have apex predators like eagles, which play a crucial role in keeping the ecosystem in check, with no natural enemies. These different levels we see here, from producers to apex predators, are what we call as trophic levels. Think of them as the building blocks of our ecological pyramid, each playing a unique role in our ecosystem. Now let's explore how the energy flows in our ecosystem. Gross primary productivity is the total energy captured by producers like plants through photosynthesis. Let's take it as 100 units, representing the total energy they capture. But here's the catch: according to the second law of thermodynamics, 90% of this energy is either lost as heat or used in various metabolic processes like respiration, leaving behind only 10%, which becomes the net primary productivity, that is, energy available for the next trophic level after accounting for the energy used by producers for their own metabolic processes. As we embark on our exploration of energy flow in our ecosystem, consider this. At the producer level, where a total of 100 units of energy is captured, only 10% will be transferred to the next trophic level. And again, only 10% of that will proceed to the next. This relentless decrease in energy as we ascend through the trophic levels shape our ecological pyramid. That is, broader at the base, representing high energy flow or abundance of energy at the producer level, and narrow towards the top, representing consistent decline in energy flow as we ascend from one trophic level to another. Now let's explore the consequences of this energy distribution, high at the bottom and dwindling at the top, and see how it shapes our ecosystem. Abundant energy at lower trophic levels supports a greater biomass and a higher number of species. Producers like plants have ample energy which sustains a diverse array of herbivores and other primary consumers. Higher trophic levels benefit from the stability created by the abundance of energy at the lower levels. This stability ensures a consistent food supply for predators and help maintain a balanced predator-prey relationship. With less energy available at higher trophic levels, organisms at these levels tend to be more energy efficient. This energy efficiency is crucial for their survival as they must make the most of the limited energy they receive. Scarce energy at higher levels limits the number of individuals that can be supported. This acts as a natural population control mechanism, preventing overpopulation of higher trophic level organisms. The flow of energy influences nutrient recycling and ecosystem health. Abundant energy at lower level ensure robust nutrient recycling, benefiting the entire ecosystem. In this way, nature provides a balance in our ecosystem, and some species play a very crucial role in maintaining this balance. These are called keystone species. They maintain this balance by controlling the populations of other species. Their presence enhances biodiversity and ecosystem stability. Removing keystone species can lead to ecological imbalance, habitat destruction, or reduced biodiversity. Some examples of keystone species are bees. As pollinators, bees are keystone pollinators essential for reproduction of countless plant species, which in turn support diverse animal life. As you can see in the middle of the ecological pyramid, I have provided you a linear representation of relationship between species at different trophic levels. For example, grass is eaten by grasshopper, which is a primary consumer, which is eaten by frog, which again is eaten by a snake. Now, this linear representation of organism at different trophic levels is called a food chain. Now, this is a food chain that you generally find in a grassland ecosystem. Now, let's have a look at another food chain from the aquatic ecosystem, eaten by zooplankton, which are eaten by small fish, which becomes a prey of a larger fish. Now let's connect these two linear food chains to create a food web. Grasshopper can also be a prey for a small fish. Frogs can be consumed by larger fish. Additionally, snakes may also feed upon small fish. Now, this interconnected network of species interaction, where multiple food chains overlap and connect, forms a food web. It showcases how various organisms in an ecosystem can have multiple interactions with different species, leading to a complex and realistic representation of energy and nutrient flow in nature. Now that we have discussed the flow of energy in ecosystems and ecological pyramid, let's dive a bit deeper into how we visualize relationship within ecosystems. We have primarily focused on the flow of energy, which gives us insight into energy flow. However, there are two other essential pyramids that provide additional perspective on ecosystem dynamics: the pyramid of numbers and the pyramid of biomass. The pyramid of number, as the name suggests, represents the number of individual organisms at each trophic level in an ecosystem. In an ecological pyramid, the number of individual species at the bottom is high due to abundant energy availability, but as we move up the pyramid, the energy decreases due to the competition, leading to a decline in the number of individuals at higher trophic levels. It helps us understand the population structure and distribution of species within a food chain or food web. On the other hand, the pyramid of biomass focuses on the total mass of living organism at each trophic level. It provides insight into the physical abundance of living matter, while the general rule is that these pyramids are always upright, that is, broad at the base representing high amount of biomass, number or energy, and narrow towards the top. But there are few exceptions when it comes to pyramid of numbers and pyramid of biomass. For example, unlike the pyramid of energy, which typically narrows as we ascend the tropic level, the pyramid of number can vary in shape. Consider a tree as our producer. It supports numerous herbivores like insects, which in turn can sustain a smaller population of predators such as birds. In this case, the pyramid of number may not have the classical pyramidal shape but could resemble an inverted pyramid, a column, or even an irregular shape depending on the specific ecosystem. Similar to the pyramid of number, the pyramid of biomass may not always mirror the pyramid of energy. For instance, in a marine ecosystem, phytoplankton, tiny photosynthetic organisms, can form the base of the food chain. While they are numerous, they have relatively low individual biomass. When zooplankton feed on phytoplankton, their biomass may be lower than that of phytoplankton due to the energy lost during consumption. Yet, the higher trophic levels, such as fish, might have a greater total biomass compared to the zooplankton. It's important to note that while these pyramids offer valuable insights, real ecosystems can deviate from these idealized representations. Now that we have discussed ecological pyramid and its component like producers and consumers, it's crucial not to overlook another critical player in this ecosystem, that is the decomposers. They play a vital role in maintaining the delicate balance of our natural world. As the producers grow, they absorb essential nutrients from the earth and its surrounding atmosphere, which fuels their development. When these producers and consumers eventually reach the end of their life cycle, the decomposers, such as fungi and bacteria, step in to perform a crucial task. They break down the complex organic matter left behind by these organisms, returning it back to Earth or releasing it back into the atmosphere. This process of nutrient recycling is essential for sustaining life in the ecosystem. It ensures that valuable nutrients are made available once again for new generations of producers to flourish. They are the recyclers that keep the circle of life turning, ensuring that our ecosystem remains healthy and in equilibrium. For a deeper dive into how decomposition works, you can watch my comprehensive lecture on decomposition. The link is provided in the description below.